SAS visual data mining and machine learning encompasses many tools, including those for data preparation, interactive model building, defining modeling flows with pipelines, managing and deploying models, etc. Model Studio is a component of SAS visual data mining and machine learning that aids in defining and automating modeling with pipelines. It includes nodes that can be added to pipeline flows for building various models and eventually comparing them to pick the best model. The open source code node is new in Model Studio 8.3 and will be available in July 2018. It supports the Python and R languages and requires them and any necessary packages to be installed on the SAS compute server, which is the engine that runs SAS code. The open source code node downloads a data sample from the SAS Cloud Analytics Server, also known as CAS, to the compute server during execution. This data transfer happens with comma-separated value or CSV files. The user can choose to work with CSV files, but for convenience, the node also makes these data available as a data frame. Let's start by describing the setup steps for the open source code node. As I've already mentioned, Python and R have to be installed on the compute server. The node itself is agnostic to the version of the Python or R installed. That is, any version can be used as long as the code written in the node editor matches the installed version of the software. I mention this because the syntax for Python 2 and Python 3 is slightly different and sometimes not interchangeable. To make the node accessible to all users, Python and R should be installed with administrator privileges, and the directories where the executables Python and R script reside should be placed in the system path. On Windows, the system environment variables Python home and R home can be defined as an alternative to point to these executables. Now let's get into the node details. The open source code node is located in the miscellaneous group as shown, right above the SAS code node. You can place this node in the preprocessing group as shown in the leftmost flow, or you can move it to the supervised learning group as shown on the right. When you have modeling node that trains and makes predictions, you should move the node to supervised learning. We will get into those details in a little bit, but first let's talk about the node properties. In the open source code node, you can choose Python and or R by using the language property. Use the data sample group of properties to select how much input data and what kind of sample needs to be downloaded when you execute this node. Getting into the details, the data sample is downloaded as a CSV file from CAS. Remember, Python and R are installed on the compute server, so data has to move from CAS to the compute server for the node to do its work. So be sure to use caution and avoid moving large amounts of data. By default, a stratified sample of 10,000 observations is created based on the partition variable and the class target when applicable. Be aware that the open source code node is working off a sample here. This would become important aspect to consider if you choose to compare this node with other modeling nodes in the pipeline that use full data. Use the Open button in the node properties to access the code editor, where you can type in Python or R code. As you can see, the code editor has a fair amount of context highlighting for readability. The variables that you see on the left-hand side are created by the precursor code. You can hover over the mouse pointer over them to see their descriptions. So what is this precursor code? During node execution, various code snippets are generated and put together before and after the user code as shown in this slide. What snippets get added somewhat depend on the node properties. So why are these code snippets needed? The simple answer is for convenience. Let me show you an example. This is the first part of the precursor code. You can see a sample both in Python and in R. It defines variables like dm_node_dir, which represents the transient working directory of the node during execution. dm_dec_target has the name of the target variable. dm_class_input contains a list of categorical variables in your data. As you can see, these are convenience variables that you can use while coding in Python or R. The node properties include a generate data frame property that is selected by default. When this property is selected, the second part of the precursor code is added. What this code is doing is converting the downloaded CSV input data to an R data frame or a pandas data frame in Python. Again, this is for convenience. In R, all the categorical variables are also converted to factors as part of this step. The posterior code snippet, as the name implies, is added after the user code and converts the data frame containing predictions back to CSV so they can be uploaded into CAS for model assessment. What I mean by model assessment is the computation of model fit statistics like misclassification rate for binary or nominal targets or mean square error for interval targets. So in summary, when you run the node, the actual code that is executed is a combination of the precursor code, the code entered by the user in the code editor, and the posterior code. Now let's look at the node results. After the node executes successfully, you can view them by right-clicking the node and selecting results. In the R example shown here, two output files are generated after a random forest model is trained. The rpt_forest_mse plot file is a PNG or image file that plots the mean square error during training, and the rpt_forest_imp.csv file contains variable importance in a CSV or tabular format. After successful execution, they show up like this in the node results. There are two reasons why the output from Python or R execution can be viewed in the node. First, output file name should be saved with an rpt_prefix because this tells the node to display them in results. And second, the file extension has to be CSV, TXT, PNG, JPEG or GIF because this tells the node how to display them. CSV files are displayed as tables, TXT files are displayed as plain text, and PNG, JPEG and GIF files are displayed as images. Now let's look at what it means to move the open source code node to supervised learning. To reiterate, the open source code node can be executed in the pre-processing group or supervised learning group. What that means is that you can do pre-processing work in this node or you can build supervised models. Typically, you move this node to supervised learning to perform model assessment and model comparison with other modeling nodes in the pipeline. For this to happen, you need to ensure that model predictions are saved in the dm_score_df data frame if the generate data frame property is enabled, or in the node_score.csv file if generate data frame is disabled. In addition, the prediction variables in this data frame or CSV should follow a naming convention. When the target is interval, the prediction variable should be named p_target variable name, and when the target is categorical, the posterior probabilities for every level of the target should be generated with the naming convention P underscore target variable name followed by the corresponding target level. For example, if you have a binary target variable called bad with levels 0 and 1, the variable names of the posterior probabilities should be P underscore bad 0 or P underscore bad 1 respectively. When the open source code node is in supervised learning and prediction data and variables are named as mentioned in the previous slide, then you should see additional charts in the node results and perform model assessment. These charts include lift, fit statistics, ROC for binary target, etc. In supervised learning, the node also performs model comparison. That is, you can compare Python or R models with other modeling nodes in the pipeline. There is one point I want to emphasize here. If your data are big, the open source code node will download a sample and train by using that sample, while other nodes will train on the complete data. In this scenario, if you are comparing models, you need to be aware that the number of observations in the validation data used for comparison might be different for the open source model compared to the other models in the pipeline. In summary, the open source code node supports both Python and R languages. It can display results, it can produce assessment statistics, and enable you to compare your model with other models in the pipeline. What the open source code node cannot do is be part of an ensemble. It cannot support registering to a database, publishing to Model Manager, or the ability to download scoring code or scoring APIs. This is because there is no compatible scoring code available for this node.